Okay, I had a video request starting with this problem out of the homework. And all of these problems, you have to realize it's a bunch of vectors, adding vectors together. So the motion of each point on this tire is going to be a combination of both the entire tire moving forward, which is what the center point here is doing, and the tire rotating. So if you add these two vectors together, the whole thing going forward, translational motion plus rotational motion, these two vectors add to the overall velocity of each point on this tire. So if we walk around the rim, and I won't solve what is in the quiz for you, so we'll go ahead and I'll put on maybe a different point. So let's start with something simple like E or B, and then I'll do one that's at some angle so you can see kind of a neat cross product relationship too. So instead of V equals R omega, you actually do omega cross R. We'll get the X, Y, Z components of your velocity on here. But let's go ahead and start out. Let's see, where's a nice bright color? I'll use orange for Halloween. Okay, so I'm gonna, instead of putting the velocity over here, let's try and get the velocity of this point here. So I'll call it, I don't know, point G. Let's call this point G. And there's going to be 2 points for this. So if we say the overall velocity of point G, and this is a vector, it's going to have X, Y, Z components. It is going to be a combination of the entire wheel going forward, so velocity of A, and this is going to be in the X direction, right? So if we have some vector and if it has X and Y and Z components, so we know the X velocity is, we'll call this the X direction, right? So the entire thing is going to be here in the X direction. So that's the translational motion part of it, and then adding on to that, we will look at the rotational version of it. So if you kind of ignore the street for this, let me just clip that off here so we can ignore it. So if all this tire was doing was just spinning in midair, it wasn't actually driving down the road, it was just spinning, and you looked at the velocity of some point on the edge of this, and maybe you knew the angular velocity, so radians per second. So you have some kind of a radians per second, and you also know the radius of this thing. So if the diameter is 22 inches and the radius is 11 inches, and it's good to put this stuff in, use feet and seconds when you're dealing with English units. So the overall velocity of this thing, it's going to be traveling tangent to the outside. So in this case, it'll be going straight up. And this is the velocity of, we called it point G with respect to A. And that velocity is going to be going straight up in the J direction. And it is equal to omega cross R. And this is, I think, a little bit new for you guys as well, to, instead of just saying, oh, it's R omega and that's the magnitude, if we crank through the cross product of this, it will actually get us this J direction. So R is going in the negative X direction, and omega, so when you talk about rotational motion, the vector that describes rotational motion is actually describing the axis you're rotating around. So if we have some kind of a X, Y, Z coordinate system, kind of like this, and this guy is rotating around an axis that is here in the Z direction. So in 2D, the rotation is always in that Z direction motion, and you're going to use your right hand rule So wrap your fingers around the z-axis in the direction of that rotation, and your thumb will point either into the board or away from the board. So in this case, omega is in the negative z direction. So let me crank through this cross product in Mathematica so you can see how this direction falls out of the velocity. And once you see it in this kind of simple scenario, then we'll be able to go and do some more challenging scenarios. But cranking through the cross product, I think, is going to be the easiest way to do this stuff. So I'm going to go ahead and just clip this, edit, copy, paste into here. Let's see, for the homework problem, I told you that the velocity of the car was like, I don't know, I think it was 100 miles an hour. So let's go ahead and use that for A here. So I'll go ahead and clear out variables. Let me change the size of this thing. Okay, so I'm going to clear out the velocity of point G, the velocity of point A, the velocity of point G with respect to A, I'll just call VGA. And we'll say the velocity of A, and we'll give it 100 miles an hour to the X. So how you do vectors in Mathematica is you just use these curly brackets and put in the X, Y, Z. So in this case, A is going directly to the right, so we can fill in a velocity of 0 in the Y and Z direction. And if we have like 100 miles an hour, so we'll have to change that to feet and seconds. So I'll go ahead and put in 5280 feet in a mile and 3600 seconds. If I evaluate this thing, yeah, it gives me a fraction. To go from a fraction to decimals, you can either turn it into a number with //n, or an easier way is if I use something other than an integer in here, so instead of 100, I say 100.0, then it'll give me decimals. Okay, so that's the velocity of the car, which is also the velocity of point A, and this is in feet per second. So that's going to be one piece of our equation. So the final thing that we're after is velocity of G is equal to velocity of A plus the velocity of G with respect to A. So that's the X, Y, Z components of this first piece. Okay, the next piece of it, this is the rotational motion of the tire. And the overall motion of G is going to be a combination of this. Let me just draw that in here real quick. So the overall velocity of G, we're going to take the velocity of A going straight forward, and G with respect to A. I'm going to add these guys head to tail, so that the overall motion of G is going to be some combination of the thing going forward and the thing rotating. So that would be the overall direction of that velocity. And we'll crank through those. Okay, so let's go ahead and just get G with respect to A. And instead of cranking through R times omega, first we have to figure out what omega is. Okay, so B is equal to R omega. Omega equals V divided by R. This is what our velocity is, and we look at this, so omega is actually going to be in the negative k direction. So omega is equal to nothing in the x direction. It's not rotating around the y-axis. It's rotating around the k-axis, and the magnitude of that is going to be the velocity of A divided by R. And in this case, let's see, if the diameter is 22, then radius is half of that, so 11 inches, and we'll make sure that everything is in feet. Okay, so there is the x, y, z components of our angular velocity. So this is radians per second. Instead of meters per second, radians per second. It's how the angle is changing with time. And it's rotating around the z-axis, and we're going into the board, so that would be negative. Clockwise is negative. Next up, so g with respect to a, what we're going to use with this is velocity equals omega cross r. So this is a cross product, just like you used for moments. So r cross ma, or angular momentum, r cross mv. It's going to be a cross product. And what this will do is it will crank through and give us the actual velocity of this point going up. So if we look at the XYZ positions of R, so from the axis of rotation to the point we're interested in. So in this case, we're going from point A over to this point over here. So we're going in the negative X direction. So let's go ahead and define R. So we say negative 11 divided by 12, right? That's our R. We're just going straight to the left. That's why it's easier to do one of these points first, that we're not in an angle. We're just going straight over. And if I put these two together, so velocity of g with respect to a, and I'm going to go ahead and do a cross product of that. So it'll be omega, and I could just type in omega here, omega cross r. And if you crank through this cross product, what you will get, oh, whoops, I had r as a vector up here, and r is just a number here. So I need to undefine that. So let's just leave it down here. Okay, so here is the velocity of that point G relative to A, and you'll see that the X, Y, Z components cranking through this omega cross R will give us the X, Y, Z components of kind of the rotational piece of this thing. So if you look at this, G with respect to A, so this is how that point is moving with respect to the hubcap, and that motion is always the rotational piece of it. So walking through this cross product, it shows us that that velocity is going straight up in the air. So this is kind of a good way to deal with vectors, rather than, you can figure out the direction of this thing by studying the image and drawing angles and figuring out what direction it's going in and using SOHCAHTOA to split vector into XYZ components. Or you can use kind of the cross product method and crank through that to get the position of it. Okay, so we have velocity A in the X direction, G with respect to A in the Y direction, and now we would like to see the overall velocity of this point G. So now that we have each of these guys defined, all we have to do is say VG is equal to VA plus VG with respect to A. And this will actually pull the XYZ components in here for VA. It'll pull the XYZ components here that we got out of our cross product. It will add those two together. And in this case, it's not very exciting, right? We just have, here's the X component, and here's the Y component. Okay, so that's the simple scenario for something that's going straight up. How about if we have something where instead of getting the velocity, let's use some angle like this 30 degrees. Okay, so I'm going to, again, choose a different point here. Let's go ahead and, I don't know, I'll choose a point down here. And we can make this point at, let's see, what angle shall we do this at? I'll do it at, I don't know, 40 degrees maybe. Okay. So if I'm trying to find the velocity of this piece down here that's at 40 degrees, I should have, let me switch images around here. Okay, so let's have this new point, and we're going to figure out what the velocity of that new point is. So I'll just call this point P. So the velocity of point P is going to be equal to the velocity of point A again. So we're going to be adding together translational motion plus, and then remember the rotational motion, we're not worried about it going forward anymore. We're just considering what this guy is doing with respect to A. So we have the point down here. This whole thing is rotating forward. So here's our angular velocity. And if we look at V equals omega cross R, so here's our radius. And in this case, our radius has its negative y, negative x. So we're going to have to split it into its x and y components. And then the overall direction of the velocity is tangent to this tire. And that velocity is also going to have x component and a y component. And if you think about how that angle is going to translate around, so this is 40 degrees. It's tangent to the circle, so this is 90 degrees. As this is 50 degrees, right? 40, 50. And this is going to be, you can walk around kind of this whole thing. So if I have 50, right? If I just look at kind of walking around this thing, and then I have 90, and then I have 40 over here. So the direction of the overall final direction of this thing is going to be 40 degrees, and you can solve for the vector this way by just looking at the picture and knowing velocity is tangent, and then you can figure out that direction and the x and y components of it. Or we can walk through the cross product. So we're going to do omega cross r again for that relative motion. So this is the velocity of this point relative to the center of the tire. So let's go ahead and we'll split up the omega and xyz components again. This time our radius has x and y components. So this will be just a little bit trickier to get. But then once we have the x and the y components here, we're going to add these two vectors together. So we're going to add velocity of A, which is again just straight here in the x direction. If I can draw a straight line. So yeah, here's our VA that's in the x direction. We're going to add that to this vector. So when we add these vectors together, so head to tail, the total velocity of this point here is going to be it's a combination of translational motion and rotational motion. So if it wasn't rotating, then every part of the tire would have just this forward velocity, right? But it's not just going forward, it's also rotating. So this is, yeah, for all of these problems, if you can understand what the tire is doing, you'll understand all of it because it's always just these two components added together. Okay, so let's go ahead. I'm going to copy this into Mathematica. We can crank through some numbers of it. And let me try and get a better snip here. Okay, there we go. Edit, copy. And here was our old one. So we'll put the new scenario in here. And let's see, I'm going to use the same velocity of A, the same omega. The only difference here is going to be this point with respect to A. So in this case, let's go ahead and say velocity of our new point with respect to A is equal to the cross product of omega, Control C, Control V, cross r, our x, our y, our z. And in this case, if you look at where our position vector is, so from the axis of rotation to the point we're interested in, we're going down, negative in the y direction, and negative to the left in the x direction. So down the y piece, that's going to be adjacent to the 40 degrees, so cosine, and then x is opposite that. So our x, we're going to take kind of just the magnitude of that radius. So the x component is negative r sine of 40. And then the y component of this is going down, and that's adjacent. So we'll use cosine 40. And we're in 2 dimensions, so we don't have to worry about a z component. Okay, so if we crank through this cross product, what we get is something in the negative x direction and the positive y direction. So if you look at the overall, this P versus A, so this is the omega cross r, velocity of this point, and we're going negative in the I direction, positive in the j direction. And if we do x squared plus y squared, we could get the magnitude of this overall velocity. But let's go ahead and just leave it in ijk components, because we're going to be adding these 2 vectors together to get the overall velocity of what this point over here is doing. So now that we have everything into ijk components, so here's the forward velocity of the car, so you'll notice that I direction, and then here's the rotational motion. So this is adding in the rotational piece of it, and if you look at, it's going forward faster than the I component of the rotation. So the overall direction of this is going to end up being positive in the I direction, and then also positive in the j direction. So let's go ahead and do this. Velocity of the point is equal to translational motion plus rotational motion. So if I add these 2 vectors together, that is the overall velocity of that point. So positive I, but mostly in the j direction in this case. Okay, so hopefully that will help you walk through that problem. And if you can really understand this one, it should help you in some of the other problems as well.